problem with the computer. Okay, Pak. So this is the very nice poster of this webinar. Now, for our friends in Malaysia who hasn't been able to travel to Makassar, now you can see the map of Makassar, Indonesia, and Malaysia. Take a journey from Perlis or Kuala Lumpur down to Makassar. Takes you about 2.5 or 3 hours by plane. And then one of the university in Makassar, among others, is Universitas Negeri Makassar. And that's the building that you can see like a ship. And then the just finished last year our new building in MIPA faculty. So now this building has been occupied, and a lot of people come to see the unit of this building. All right, now let's for our discussion today, I hope that I can cover at least four main topics. First one is let me introduce a little bit about our work on geopolymer in ONM, because geopolymer actually in our university become uh, one of the excellent research topic that funded by the government. So it's become a priority for ONM to develop these materials. That's a good news actually, unfortunately, because our staff are still very limited working with me on geopolymer. But I hope that with the graduation of some of our masters and even PhD students from other universities, they will join us in the next few years to develop these materials. Second, we will discuss a little bit about the main sources and synthesis of geopolymer. Then I will focus only on metakaolin because we cannot cover the whole sources like fly ash or blast furnace or laterite materials in order to present the results of geopolymer by using those materials. So let me focus mainly on metakaolin. And the third aspect that we can discuss is about the what is the uh, relationship between physics and material sciences, particularly in the study of geopolymer. And then I will close this presentation by introducing and suggesting new trend on multifunctional geopolymer composites. So this is the roadmap actually of ONM geopolymer research. We need a lot of explanation for this actually. We start intensively on geopolymer research in 2007 by utilizing the local clay, which is actually laterite. and we produce a very simple bricks materials, and we call it a low temperature bricks. And we, at that time, the source of fly ash in our area, it's only from one of power plants in Portland cement production, around 70 kilometers from Makassar. And the fly ash is a type of class of uh, C, I think, because it is very quick to set in, and if we make it in a big or large volume, then sometimes we cannot cast it, and it become set in, become hardened. So we learned from that time in 2007 to produce simple bricks, ceramics, and refractories. We still remember that the refractory that we produced in 2007 or 2009 were able to uh, resist the fire with a temperature around 850 to 1000 degree Celsius. So we feel that if we add the pure geopolymer with other inorganic materials, then we should be able to extend the temperature range of the refractories. And we struggling with those research until we try to incorporate the nanomaterials like MgO, nanoparticles, as well as the zinc oxide nanoparticles, and then the temperature can rise a little bit to 1100 or 1200 degrees Celsius, but still introducing a lot of cracks on the surface and the bulk of the materials. And in 2010, 2012, especially with the collaboration with Professor Hamza Pansuri of ITS, we consider geopolymer as a materials for heavy metal immobilization. So this is a very, I still remember the time that we study those aspects, and Prof. Hamza has to travel to Makkah for Hajj, and I have to represent him as a second researchers to present the result of our research in order to encapsulate the chrome and cadmium ions in the network of geopolymer. And we continue that project until one of the PhD students of Prof. Hamza Pansuri graduate. I can't remember, maybe 2015 or 2016. Can't remember the time. And then we developed geopolymer with the introduction of organic and synthetic fibers, natural, call it natural or synthetic fibers. We use pandan fibers. We use even we use coconut trunks fibers to produce a natural fibers, and become enforcement of the geopolymer metrics. And it is the result is very encouraging actually. We still need a lot of studies in order to make the composite fulfill all the criteria to be standardized as a good composite for structural applications. In 2016, 2018, we start looking at the high definition geopolymer surface, uh, inspired by the materials that can actually absorb moisture as well as can resist bacteria and other organic stuff. So we use the organic materials, and then we see the effect of the geopolymer as an antibacterial uh, agent, like the introduction of uh, uh, silver nanoparticles, TiO2 nanoparticles, and then later we introduced the materials like chitosan and hydroxyapatite until now. So this research is still uh, running. Some of my students actually still looking some aspects of this high definition geopolymer surface. And starting from 2019, together with Prof. Hamza again, we see the opportunity, we see the possibility of geopolymer to be a good membrane materials. We start separating ethanol with water by using a perforation system. And in 2021, we used that kind of system with the same or similar membrane to separate the salt from the seawater. So we produce fresh water by using a perforation system. But until now, the fresh water quality or the salinity of the water is still below 70%. But we hope that by the time we develop the membrane, geopolymer membrane, we can reduce the salinity up to 90%. So, and then become acceptable as a fresh water. So that's the research that we are conducting at the moment, and at the same time we propose two or three new projects related to geopolymer. The first one is how can we harvest the energy, especially thermal energy, by using geopolymer, utilizing the Seebeck effect. And secondly, we will use geopolymer as electromagnetic interference shielding materials. I will explain this later as a part of my talk today. All right. Now let's remind some of you actually, because I think most our attendances today already have a good background on geopolymer research, that the main sources of geopolymer is actually aluminosilicate minerals. And here I can I can show you at least three main sources of geopolymer. First one is the haulinite and laterite. Very quite similar actually between the hauline minerals and the laterite. The only difference is because laterite is very rich with iron and other metals, ions like MgO. Uh, Sometimes it contains also chrome, contain even some laterite from South Sulawesi. It contains molybdenum in small part. We also have this is a very nice fly ash actually. You can see the morphology of the fly ash particles. Some are very small actually, less than 1 micron, and smaller than that. We know the type of the materials, the cenosphere. Some research, our colleagues from other universities start using cenosphere to produce geopolymer. It seems to me that the results quite nice, but it requires a lot of effort in order to separate between the large particles with the small particles in fly ash. But if you can do that, then of course the quality of the materials will be much better because the solubility of the fly ash, of course, will be higher when the particle size becomes smaller. And blast furnace, like you can see, the morphology is not it's not uniform, like chunks of materials. Uh, Very different with the morphology of fly ash. The geopolymer world actually is a part of inorganic polymers. This is you can see the position of geopolymer as a cementitious materials. It's a part of the alkali activated materials. So geopolymers actually is a very special topic in alkali activated materials. And that's why if we see the production of alkaline cement, we can actually divide it into two main materials. First, if the materials contain a high calcium, then we will call it, the term of the CASH material, so alkaline cement. And if the starting materials contain a very low calcium, then we designate it as NaSH materials, and we call it alkaline inorganic polymer, or simply geopolymers, as first introduced by Professor Davidovich from France around at the end of 1970s. So, and these materials developed so rapidly after the introduction of geopolymer by using fly ash around 2000. I still remember some early researchers on these materials like Garcia, Polamo, Van de Venter in Melbourne. They start utilizing fly ash as a starting material instead of metakaolin. And since that time, the research development of geopolymer increased rapidly every year, and the publications of the result is huge. It is very difficult to discriminate between one paper to another in order to find the fundamental or the basic properties of geopolymer. And in 2015, Garcia et al. Produced a very nice paper concerning the theoretical work of the geopolymer network. This is along with the study uh, of fundamental team in Melbourne, actually, with Professor Profis at the time. Now, in terms of physics related study in geopolymer, we can see that most our concern is not on non-structural applications of geopolymer, but more deep on the uh, structure, the properties, and the characterization of these materials. Uh, we may apply, or we may study the performance of these materials, but only very limited on the laboratory scale, because most physicists, I think, are not able to make industrial or scale up the research result in order to be feasible for industrial applications or large applications. So physicists are very limited actually in terms of the study, because they will stop in laboratory scale. So most our research related to the processing of the raw materials, and then producing these materials by using a simple chemical uh, uh, reaction. And most physicists actually has to learn from our colleagues in chemical or chemistry department in order to understand the materials properties and the reactions mechanism. Yeah, in order to to make the right composition of the geopolymer. And I think Prof. Hamza still remember the time when I start my research on geopolymer. I have to learn from him a lot of things about basic chemistry until I have a good background on the physics and chemistry of the geopolymer. So the relationship between structure, properties, processing, and performance is a very unique and open a lot of opportunity to our student to explore. It's a very rich area to study. Let me give you an example. If you have a kaolin, for example, so you see the kaolin here. I learned this kaolin actually from geology department. I have a good friend at Curtin University who graduated from geology department and specialized in kaolin. He explained to me a lot of aspect of these fascinating minerals, as well as taught me how to characterize them by using at least three main instruments or techniques. And he said to me, if you want to know the chemical composition of kaolin, then you have to use XRF. At that time, 13 XRF are very big and very old actually, but the result is very good. So this is one of the example of the kaolin that we use at that time, supplied by one of the kaolin supplier, Kingsley White Limited, actually, incorporation in Perth, Australia, and we characterize the kaolin by using the XRF available at 13, and we found the result is quite similar with the result provided by the supplier. And he asked me as well to study the structure of kaolin by using XRD. I learned XRD together with Professor Hamza at 13, and we got 5 machines at a time. But he asked me to focus on the Hinckley index, because this index determines the quality of the crystallinity of the kaolin. The Hinckley index range from 0 to 1, and if the perfect crystals will have Hinckley index equals to 1, but no such things that occur on the nature. So all the Hinckley index below 1, mostly around 0.7 to 0.8 at the most. And I also use the FTIR in order to see the functional groups of the bond between one species to another in kaolin minerals. And you can see the highlight of the spectra of FTIR, where you got the band of water bending, you got the silicon-oxygen-silicon stretching, the silicon-aluminum stretching. So the FTIR will give you, the easiest as well as the fastest information about the quality of the kaolin that you use, whether it has a perfect bond between silicon oxygen and silicon, as well as silicon and aluminum bond at certain wave numbers. So that's my first impression actually on kaolin, that these materials, in order to know whether, then you have to use at least these 3 instruments together to find or to make sure that the quality of kaolin is suitable as a geopolymer precursor or starting materials. And then we move to a more advanced characterization of geopolymer by using electron microscope, scanning electron microscopy, as well as tunneling electron microscopy. At that time, actually, we used Philips 300 SEM at 13, and I'm sure that Prof. Hamza still remember that machine running together with Miss Elaine. And then we study the morphology of kaolin, and we need a lot of effort in order to get a very nice crystal appearance of kaolin that can be published, because the preparation is one of the most crucial things when you study things by using scanning electron microscopy. So you see the morphology of kaolin forming a hexagonal system with a thickness less than 1 micron. And then we, because this microscope is coupled with the energy dispersive spectroscopy, so that you can take the X-ray adducts of the materials. Then you got the EDS spectrum. You see the composition, the main composition of the kaolin is aluminum and silicon, 14% and 16% of silicon. So silicon is a little bit higher than the aluminum. So this is a 1-to-1 ratio between silicon and aluminum atoms, so which is a good things or good materials to produce a geopolymer, starting from the silicon aluminum ratio 1-to-1. Then you can increase the ratio by adding some materials, silicon source materials, or even aluminum source materials, in order to change the ratio of silicon to aluminum. And if you are doing your research on geopolymer and you are on master's or PhD study, then I suggest you to learn and use transmission electron microscopy. It's a very important instrument in order to study geopolymer in advanced area, because you can find the image of the materials down to resolution of 0.1 nanometers by using transmission electron microscopy, which it's impossible to achieve by using scanning electron microscopy. Besides that, if you use transmission electron microscopy, then you can also study the electron diffraction of the materials, especially if you incorporate your materials with crystalline materials, or if you want to study the surface of geopolymer by using low energy electron spectroscopy, then TEM will provide you the best opportunity to study in depth scale of geopolymer. Probably you can reach the depth of from the surface of geopolymer around 1 micron or a little bit deeper than that. So you can see if you coat, for example, your geopolymer with other materials, and then you study the surface of geopolymer, then the best instrument that you need to study that surface is by using transmission electron microscopy. Now I feel I miss actually this machine because the last time I drove this TM is about around 2005, and since that time I haven't had any opportunity to use them again. So this is a TM Geo 2011. They are available at 13 University when I did my PhD. Now, because kaolin, has a very low reactivity into alkaline environment, and in order to improve the reaction with the alkaline environment, then kaolin need to be transformed into a metakaolin. So from a crystalline paste into amorphous phase by the hydroxylation process or calcination at 750 degrees. Most researchers actually use that temperature, but some people suggest a little bit higher than that, around 800 or 850. But some researchers also found that using 650 degrees Celsius for 4 hours should be enough to transform the kaolin into a good metakaolin. So I did this research by fixing the hydroxylation temperature at 750 degrees and holding around 4 hours. And then I examined the morphology by using the scanning electron microscopy. I found that most of the morphology of metakaolin are still similar with the morphology of kaolin. It makes that the kaolin morphology is reserved during the hydroxylation process, but the phase has been transformed from crystalline phase into amorphous phase by confirming this result using X-ray diffraction. So you can see the transformation from crystalline into amorphous state here you can see, but there's still a lot of small peaks on the surface or on the bulk of the metakaolin, uh, especially anatase and quartz, which cannot burn or evaporate at 750 degrees Celsius. So it's not 100% amorphous actually. It's still, you can see a semi-amorphous materials because there's still a lot of crystalline phase. It's very difficult to find a kaolin without any quartz or anatase inclusion, because you know that the kaolin is a mineral produced by weather change in the environment. So there's a lot of materials that react with the silico-aluminate uh, during the uh, climate change for a long, long time. You can also confirm the phase change of the kaolin by using the FTIR. You see the spectra of kaolin and metakaolin, and you will see especially the presence of water much less in metakaolin, because 14% actually of bulk water of kaolin will be evaporate around 750 degrees Celsius. And this is, to confirm this, you need to check the data of thermogravmetry and differential thermal analysis of your kaolin. So if you calculate the mass change um, of your kaolin, then you will find that the around 750 degrees here, and the mass of your kaolin will reduce around 14%. And the reduction of that mass is considered as the evaporation of bulk or zeolitic water in the network of kaolin. And the geometric diffraction, electron diffraction. You see that the kaolin morphology here, and then you take the electron diffraction, and you found that the pattern is only about rings, which means that Davidovic in 1991, if you want to produce a good geopolymer, by the activated oxide. So very the ratio, but it's not 100% or cannot be guaranteed will be successful for other materials, especially if you use fly ash or contain a lot of materials other than uh, SiO2 and aluminum, two or three. So uh, we can, of course, we can take the data from the XRF in order to see the composition, the chemical composition of the starting materials that you use, and then we can adjust the ratio. But because there is a lot of other stuff inside the fly ash or slags, then it's not always work very well. Uh, like when you produce geopolymer from metakaolin, because that's why metakaolin was considered as a more pure aluminosilicate compared to fly ash or other stuff. But anyway, that's open, a lot of study in order to standardize the fly ash in the production of geopolymer, and this is one of the main concern actually of my colleague in ITS Surabaya, Prof. Hamza and Dr. Janwarti, by collecting hundreds types of fly ash and study them to make one red line of geopolymer production by using fly ash. So they call it how we standardize the composition as well as the alkaline activator of geopolymer by studying them. So this is a big project actually of especially our friends from ITS. The production of geopolymer can be, it's always nice actually to see the development of the theoretical background of these materials. And the best that we can have are three steps of production synthesis of geopolymer. You can see the attacking geopolymer by using the uh, very high alkaline solution, and most the pH of the alkaline reach around 13, and that will break the raw silicon aluminum materials into aluminate species and silicate species. And the formation of geopolymer gel will come after the separation of the aluminate and the silicate species here. And then we will start polycondensate by a simple manual mix around 5 minutes at least if you volume material is not too high, then by the help of temperature below 100 degrees Celsius, that you should be able to produce a solid materials called geopolymer. So it's quite simple actually in the synthesis of geopolymer. Although that it's not always produce a good result because there's still a lot of parameters that you need to control in order to produce a good geopolymer. So theoretically, probably you can follow quite well, but
Dr. Subaer, uh, we cannot hear your voice clearly. Seems like the sound is interrupted.
do the experiment, then you will see there's a lot of things that you need to control. The quality of the internet at the moment, but let me check our my students here. Can you hear quite well? Yeah. Oh, okay. I don't know what happened. Is there any? Sorry about that. Uh, okay. Thank you. Thank you. So I can.
All right.
All
Sorry
right.
about that.
Sorry about that.
How about now?
How about you?
Now it's better.
All right. Okay.
Right?
Yep. Um, this is the morphology of. Okay. Sorry about a little bit the distraction of um, my presentation because of the quality of the notebook that I use at the moment. Now, after we discussed a little bit about the geopolymer synthesis, now we move to the structure of geopolymer by using at least three main machine that you can access. First one, you can use the FTIR in order to confirm that your geopolymer is uh, correct and has a high quality. Second, you can use the X-ray diffraction, and you can see the diffractograms of metakaolin on your geopolymer. You will see the hump of metakaolin here shift into a higher angle of 2 theta, it confirms that the rearrangement of uh, silicon, aluminum, and sodium inside the bulk of geopolymer, and that will shift the amorphous hum of your materials. So the X-ray diffraction actually gives you a lot of insight about the what happened actually inside the network of geopolymer. But the most advanced one, if you want to confirm that your geopolymer has a high quality materials, that you need at least one of this machine, a 27 aluminum magic angle solid NMR spectra. I remember that one of my friends at 13 has to travel to England in order to access the machine because it's not available at our university at the time. So he has to apply to another university in order to make a good measurement by using solid state NMR. So this is the result. You see this is the metakaolin based geopolymer, and this is fly ash based geopolymer. You can see the species of alumina coordinate, 4 coordinated alumina. All right, when it transforms into geopolymer, you will find the chemical shift uh, in the peak of the geopolymer. It's around 50 or 60 ppm, which is quite similar with the fly ash. So this is a good instrument, but it's not readily available everywhere. So we need a lot of efforts in order to access this machine. And if you want nice pictures of your geopolymer, and then you can use a fly ash, all right? Because this is a picture of the morphology of geopolymer taken by one of researchers in University of Western Australia, and we learn actually from him how to synthesize, how to produce geopolymer from fly ash. I still remember when we did a workshop together, and his image won the best image prize at the time at the University of Western Australia. But he covered this with a lot of colors, so to differentiate between the matrix of geopolymer as well as the unreacted fly ash particles. This is a geopolymer that I made and then polish quite deep to 1 micrometers by using a dimple polishing. And the purpose at that time actually is to produce a geopolymer with a thickness around 100 nanometers. But before I reach that thickness, then I need to take the image by using SEM, and this is the SEM that I got from the Philips 300 SEM. You see that on the surface of the geopolymer still lying some unreacted metakaolin, as well as some quartz, they already incorporated as a part of the kaolin, which is not cannot be burned at 750 degrees. So this is the latest actually research in 2019 by using laterite soils, and you can see the morphology of the geopolymer made from laterite is quite different with the morphology of geopolymer made of uh, metakaolin and flash. So this is a good opportunity actually to compare the morphology as well as other properties related to the morphology of geopolymer by using a different materials. Because of course there is a relationship between the morphology and the mechanical, the thermal, the electrical properties of geopolymer. So this is the basic information actually that you need to know, that the morphology can be designed, and the microstructure can be designed in order to meet the requirement, the performance requirements of geopolymer. Next, when you produce your geopolymer, please don't forget these two measurements immediately. So the day that you produce your geopolymer, then please remember to measure the bulk density as well as the apparent porosity of your geopolymer by using a very simple method based on Archimedes method. You just need a water, heat the water up to 100 degrees Celsius. Then you use a nice balance in order to measure the mass of the geopolymer in a dry state. When you immerse into the boiling well waters, etc., then you can find your bulk density as well as apparent porosity by using a very simple equations. And you see that the most of geopolymer that we can produce, the best geopolymer that we can produce will have, by changing the silicon aluminum ratio in the range of chemical composition that we have from our starting materials, that first the apparent porosity can reach up around 30% of your materials. All right. You can bring it as low as naturally as low as 20% of apparent porosity without doing anything, just producing and changing the silicon aluminum ratio. The bulk density, can be varied if you use metakaolin, of course. You can start from 1.1, 1.2 to around 1.7 grams centimeter minus 3. But of course, you can reduce the bulk density if you want to make more porous materials. And this related directly actually to the strength of the materials. The less pores of your materials, of course, will have a more dense, and then will have a higher strength. So the porosity will influence of your materials quite bad if you need to produce a high quality of geopolymer, strong materials, that you need to control so many variables or many parameters in order to not introducing more pores of your geopolymer. It's impossible actually to uh, stop the development of geopolymer of pores inside the bulk geopolymer, because we produce geopolymer by using water, by using the alkaline solution, and then we uh, heat up around 70 degrees or 75 degrees or even sometimes 80 degrees. So the water will eventually evaporate to the surface of the geopolymer and left behind pores, of course, or water trapped inside the geopolymer. So that's become a void of our geopolymer. But that's not always bad, because sometimes we need the porosity of geopolymer for other function. So it's depend actually on the purpose of our research. And if you want to study further the more advanced information about the porosity of your materials, then you need to access the instrument or technique for a surface area as well as pore size or pore distribution measurement by using BET method, Brunner, Emmett, Taylor, because by using this method that you can actually study the porosity down to micro, meso, and nano pores size, which is not possible to know to get the information by using Archimedes method. You can use this method BET by using liquid nitrogen intrusion, or if it's not available, then you can also use a mercury intrusion for your porosity measurement. But of course, by using liquid nitrogen intrusion, will give you a more uh, advanced information about the pore distribution for size, surface area of your materials, especially if you directed your geopolymer to be a filter or a membrane. So this is compulsory for you to study or to use these techniques to access the information of uh, pores of your geopolymer. Now let's move into the other properties that we can, confirm to know the quality of our materials by studying the thermal properties of geopolymer. Here in this presentation, at least there are two type of measurement that you can use in order to know the thermal properties of your geopolymer. First, you can measure the thermal conductivity, and secondly, you can measure uh, the expansion, the linear or the volume expansion of your geopolymer by using dilatometry techniques. And for thermal conductivity, you can use one of the best method that I feel use for long time in order to measure the thermal conductivity of geopolymer is by using the hot wire method. The You see the diagram of the materials, the setup of the experiment. Okay, you can use a very nice small chrome or tungsten uh, uh, contact, and embedded the uh, thermocouple tip in the middle of geopolymer. You can use you can make your geopolymer into a cylindrical shape or a rectangular shape for this kind of measurement. And you can vary actually the size. But when I did my PhD, I used or made a sample with the length of 25 centimeters and the diameter of 5 centimeters. And embedded the wire in the middle of the sample, and then with a special design of the mold, I can insert it the tip of the thermocouple. One was inserted in the middle of the wire, and the second you can put it a few millimeters from the wire. So it's very challenging task to produce this sample. But then when you do or when you measure the change of temperature by introducing a small current into the sample, then you will see you will have a very linear relationship between time and temperature. And from the graph that you got, then you can calculate the slope that you have from your graphs can be directly be used to calculate the thermal conductivity by using Euler equation that you can see K thermal conductivity equals to energy that you apply divided by 4 pi and divided by the uh, uh, temperature gradient as a function of time. Then you got the result, the thermal conductivity of pure geopolymer. It will change a little bit when you change the composition. For example, silicon aluminum from 1 to 1.5 to 2.0, sodium to aluminum ratio from 0.6 to 1. Yeah. So you see the change of thermal conductivity here. Second, this is a very nice experiment actually. If you have this machine, a dynamic mechanical analyzer, and I use this machine in ITS once again, thanks to our friends there, Professor Suminar, who has this access to this machine, and we got the nano, expansion of geopolymer. Very, very nice. And the result actually have been published, but unfortunately I didn't have opportunity last night to access the article, so that I just present the result that I did when I have when I did my PhD study. You can see the thermal expansion result of geopolymer. So you hear as a function temperature down to, or mostly you can only access to around 800 degree, because after that the materials will shrink quite badly, so that you don't have any the gauge access of the dilatometry has been lost. You cannot access the data anymore at more than 900 degrees Celsius. But what you can see here, the coefficient is negative. It means that the geopolymer is actually shrink when you heat it up, say from 100 degree at low temperature. For example, from room temperature to 100, the materials will expand a little bit. All right, and then it will shrink. It means that the geopolymer will solidify. The density becomes more higher, you can see there is a kink around 500 degree here. This is mainly caused actually by the aggregates. So if you put an aggregate inside the geopolymer, make sure that the aggregate you use is not the one that has a high thermal expansion coefficient, because otherwise then the materials will get cracks, or the cracks development will grow very fast at uh, around 500 degrees Celsius, especially if you use quartz. So quartz has a very bad influence on geopolymer for higher temperature application. So it is not recommended to use quartz as aggregate for high temperature applications of geopolymer. Use other inorganic minerals as an aggregate. Don't use quartz. So this is a good finding actually at the time, and we need a lot of effort in order to interpret this one, and then we discuss this result with other researchers, and then we confirm that this is because the expansion of quartz inside the geopolymer more rapidly than the bulk of geopolymer, the matrix of geopolymer itself. So it's, yeah, please consider it as one of the topics that you can explore more. The mechanical properties of geopolymer, especially for our friends who are dealing with the geopolymers as a structural materials. So this is a very important measurement, accessing the mechanical properties of geopolymer. Stress and strain by using a measurement like measuring the tension, compression, shears, and torsion, accessing the elastic deformation or plastic deformation of geopolymer, so that you can have information about the yield strength, tensile strength, ductility, toughness, hardness. So a lot of work actually, especially for our friends in CPIL, CPIL and probably in materials engineering. So, you know, for physicists, normally we made a very small sample actually, in order to just to have a good information about the compressive strength, the tensile strength of our materials, but not as complete as it should be if the materials will be applied as a structural materials, for example, for building, for road, for bridge, etc. So this is a very important measurement that you can consider when you produce the geopolymer for structural applications. I just want to show you that the influence of the aggregate in a lead scale are quite big actually in terms of the strength of the geopolymer. Let's see that you can see here the geopolymer, the influence of aggregate will reduce the strength of the materials a little bit, although the bare scale, the scale bar is still, the error bar is still, acceptable. But the most, the most influencing factors of compressive strain is the porosity, the apparent porosity. So as I said before, that you cannot avoid the formation of pores inside your geopolymer, but you can control it actually. You see the influence, the higher percentage of porosity, then the lower compressive strength that you can gain. Compressive strength, the best compressive strength that I can produce at that time is around almost 90 megapascals by using small samples of 5 centimeters in length and in height and 2.5 centimeters in diameter. I go around 90 megapascals with porosity around between 26-27%. So that's the relationship between the physical and then mechanical properties of geopolymer. Now let's move quite quickly. The one also important aspect, if you want to measure the surface, a high definition surface of geopolymer, that you need the hardness properties of geopolymer, especially by using there's a lot of actually techniques to access the hardness, but most techniques that we use for high definition surface is by using Vickers hardness measurement, and then this indenter made of diamond in the form of pyramidal indenter, square base pyramidal indenter with the angle 136 degrees, and you see the formation of indentation of geopolymer on the surface of geopolymer here. Very nice. You apply this load around 2 kilograms for 20 seconds, then you can have the hardness of your materials, and it will change as well as a function of silicon aluminum or function of sodium aluminum or other parameters you can think of. Now, the electrical resistivity of geopolymer is one important parameters that we need in order to understand the behavior of these materials, especially during especially for changing the temperature, changing the climate, because the thermal conductivity, the electrical resistivity of geopolymer will directly also influence other properties of these materials. You can use 2 or 4 probes techniques in order to access the electrical resistivity of geopolymer, and by using the alternating current with a very low frequency to a very high frequency. Say, for example, from 0.1 hertz to 100 kilohertz. Then you can have a very nice Nyquist plot that display the conductivity mechanism of the electrons of your materials, and then you can measure the electrical resistivity as a function of time by using a very simple setup of experiment shown here. So this is the one of the formula that you can use in order to measure the electrical resistivity. And this is a project that we are currently dealing at ONM. We propose this as energy harvesting sources. We want to tap the heat of geopolymer in order to produce electricity by using the Seebeck effect. So we got some information from other resources, by using kaolin or metakaolin, by using fly ash, etc. And then we will try the best in order to maximize the thermoelectrical voltage at low temperature differences. So, for example, if we can, daily light, for example, we can reach the temperature of geopolymer up about 60 to 70 degrees from room temperature, so that we have a different temperature, say for example between 20 to 30 degrees Celsius. Then we should have a thermoelectrical voltage that can drive, a small current. So this is the very nice project that we are planning now to harvest the energy from the ability of geopolymer to retain the heat inside. So geopolymer become a sink of heat for quite a long time. So this is still very early to explain actually, but if you can discuss this, in depth in the next few years until we got very nice result. And the second project that we are now working on is producing geopolymer as electromagnetic interference or EMI shielding. Because there's once you got a lot of electrical machine inside a building, then it will emit electromagnetic waves around, and then it will interfere with other devices, so that the function of the devices will reduce. And in order to avoid that kind of interference, we need a very nice, at least a wall to separate one device to another device, or at least to cover one device to another device with a good cover that will, reduce the electromagnetic interference. So this project. We already found some articles of electromagnetic interference materials by using Portland cement. But now we are trying to develop geopolymer as a composite that we can apply for this purpose. We measure the electromagnetic interference by using the nano vector network analyzer. This is available now in our laboratory, and we are on the way to do some measurements, some experiment with the frequency up to around 3 gigahertz. So this is a common electromagnetic wave frequency around us in any building. So the materials that we are going to use is still using metakaolin, but then we may incorporate with other materials rich with iron as well as carbon-based materials like graphene, or in the form of RGO, or in the form of fiber, or even graphite, for example. And then we will see how effective the materials to reduce the electromagnetic interference. So that's the formula that we are going to use. Now this is bring you to the end of my presentation. That one of the current materials that people are hunting in so many laboratories is the incorporation of geopolymer and graphene. So we have done this since 2019, and we are still studying this in depth. But we see that the quality of geopolymer added with graphene is remarkable. Uh, Now I got this some samples available with me now, and but I haven't been able to characterize them in any properties yet. But I can see that it's so tough compared with other geopolymer that I have produced so far. The surface so smooth by changing the ratio between geopolymer and the graphene. So it offers um, a lot of possibilities to explore about the function of graphene in geopolymer. And one papers that already reported very nice producing supercapacitors by using graphene. Um, you know, um, by Su and Zhang in 2017. Um, by accessing the electrochemical properties of these materials. And then they claim that they did produce a super capacitor. So if geopolymer can be applied as a supercapacitor, it means that we can, we can store a lot of energy in in our walls made of geopolymer. So imagine that you make a concrete of geopolymer, but at the same time, the concrete, function as a supercapacitor to store your electrical energy. So I imagine that actually to be happen in the next few years, that we can produce a wall as well, not only a wall but also as a supercapacitor. So let's work on this. I'm working on this actually uh, 2 years ago, and then the result is quite encouraging. We will produce the articles very soon. We visited the result at Universitas Indonesia a few times. And the last project that we are still working on is the light transmitting geopolymer by using fiber optic composite. So this already produced one thesis of my students, and then we are still continuing to make in a more nice and controllable procedure to produce the so-called light transmitting geopolymer. And now that's bring us to the end of my presentation today, and I'm happy if you have any questions to discuss. And thank you very much for all your patience and attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you. Our moderator, thank you very much. I bring back to our moderators.
Thank you very much, Dr. Subaer. Alhamdulillah. Thank you for the very informative and insightful presentation. Next, as a sign of our greatest appreciation. Just a moment, Doctor.
Assalamualaikum Pak.
Yes.
Waalaikumsalam warahmatullahi wabarakatuh.
Let me start first.
Yes. Mus, silakan.
Pak, if you can share a little bit detail about the immobilization of heavy metal using geopolymers material.
Ini kan kewajiban videonya di sini, bilang ke semua.
Pak, saya ada satu soalan, Pak.
Oke Pak, silakan Pak.
From your slide, Pak, you mentioned about the immobilization of heavy metal using geopolymer system.
Iya Pak, silakan. Sorry Pak, tolong diulang. Tolong diulang ya, oke. Bisa diulang, Pak.
Pak, dalam Bapak punya slide, Bapak ada mention about immobilization. So kalau Bapak bisa explain a little bit on immobilization of heavy metal using geopolymer material.
Ya, ya. Betul Pak. Jadi research itu sebenarnya initiated by Profesor Hamzah. I think Prof. Hamzah, we got at least 2 or 3. I can't remember. I can recite actually. But I think we got 2 publications on that area. Yeah, Prof. Hamzah, about the how to immobilize the ions actually of cadmium, chrome, and
Lead.
I think lead. That's right. Yeah.
Yeah.
By varying the concentration, I think from 1,000 ppm to as high as 6,000 ppm, if I'm not mistaken.
To 16,000 ppm relative to IS.
And the best things of the materials are it's not as bad as what we thought, and every ions has a different influence on the performance and the macrostructure of geopolymer. So, for example, chrome has a different mechanism, and with the cadmium, a different mechanism with lead. And it influenced differently, but the kinetics of the leaching can be formulated actually. So with a simple equation, and that's very nice actually to see that these materials can hold geopolymer. I mean, can hold the heavy metals inside its networks, and if you can produce that, actually, that will save the environment. So, there's a lot of papers, abundant papers, discussing the ability of geopolymer to solidify any even nuclear waste. So we can explore that, of course. So we don't, unfortunately, we don't have enough actually students to continue that study, because one of the study that we did with Prof. Hamzah 2 years ago actually has been stopped now. I don't know if Prof. Hamzah will continue that study again. But that's the impression that I have from geopolymer made of fly ash that can immobilize the metals, heavy metals. But we need to access more metals if you want to have a good trend. So that's the
kalau dia punya main kriteria untuk kita produce geopolymer material for this type application, apa dia punya main kriteria, Pak?
First, the main first criteria that we use that time, I remember that Prof. Hamzah said that we need to find the best materials which has a higher compressive strength. All right, so we produce a lot of geopolymer, varying the molar ratio of SiO2, Al2O3, so that we got the highest compressive strength. Then we we study the porosity, the bulk density, as well as the apparent porosity of the materials. We choose the smaller percentage of apparent porosity, and we see the microstructure by using the microscope, the scanning electron microscopy, and then we choose one particular composition as a basic materials to immobilize all the heavy metals that we got at the time. Probably, I can't remember, but the metakaolin based geopolymer that we produced at the time has a compressive strength between 30 to 40 megapascal. Maybe I need Prof. Hamzah. Is that right? Around 40 megapascals, right?
Yeah, it's up to 50, some
up to 50 megapascal. Yeah, okay, yeah.
And so using fly ash, it is fly ash geopolymer.
Maybe we use fly ash. Sorry, we use fly ash.
Metakaolin geopolymer maybe can reach much better, and also the immobilization also will be much better.
That's right.
It's using metakaolin instead of fly ash. Yeah, maybe
okay,
we will discuss it more detail after Raya. Yeah, Pak Mustafa.
Inshallah, after Raya.
It's related to the chemistry of geopolymer.
Yeah. So after Raya, we have one more webinar on the chemistry in geopolymer. Inshallah, we will delivered by Prof. Hamzah.
Yeah, inshallah, after Idul Fitri.
Thank you, Pak, for the answer.
Okay, Prof.
Thank you, Prof. Mustafa, for the questions, and also thank you, Prof. Hamzah, for the participation also in delivering the inputs. Any questions from other questions from the audience? We have one question from the text box, okay, we have one question. Professor Madya Dr. Muhammad Fazil Ashad has raised hand, please. Doctor, silakan.
Assalamualaikum. Thank you, Fatullah. Thank you, Prof. Mus, and thank you to our speaker, Dr. Hendras. I'm very happy to hear the presentation related to the utilizations of metakaolin to the geopolymer concrete. My question is that as long as I know the utilizations of the metakaolin will increase the cost in production of concrete or maybe geopolymer concrete. So what is your comment on that matters? Since fly ash is the considered as waste material, and then the main reason of having or using the fly ash is to utilize the waste and then the waste is considered having a what we call it some sort of geominerals. Okay, so fly ash is considered as a waste that containing geominerals, and then that is the main reason of why we are using or introducing geopolymer, because on the first place we want to reduce the utilizations of calcium in the productions of cement. Uh, but in your case, you are using the natural mineral, which is kaolin, and then you transform it into metakaolin. uh, I was thinking on the cost increment during the productions of geopolymer. So can we have any? Sorry, I just want to have any ideas on that, because just in case if others were asking us about the same issue. So please, thank you.
Okay, thank you, Professor, for very nice questions. In 2007, 2009, we tried to calculate the cost that involved in the production of one bricks similar to natural bricks made from raw clay with using metakaolin. With the same size of bricks, normal bricks, 25 centimeters in length, 7.5 centimeters in width, and 3 centimeters in thickness. It cost us about 120% expensive, more expensive than normal bricks. The reason for that, because first we use a furnace to heat up the kaolin into metakaolin, and that costs a lot of money in order to convert a lot of kaolin. And then we use activators made from silicon, made from sodium silicate, and then it takes time actually to produce a lot of bricks similar to the normal bricks. So the production of geopolymer, basic geopolymer, by using a metakaolin, it's not suitable for industrial scale. It's so expensive in order to produce the same volume of say Portland cement. It will cost us more, and therefore the best way actually to compensate that problems is by mixing materials. So we cannot use a single materials alone in the production of geopolymer. For example, just using a fly ash, or just using a metakaolin alone, or even just using granulated blast of furnace slags, for example, or even laterite soil. So what we did, we try is to mix the materials. For example, we mix the metakaolin with laterite, we mix metakaolin with fly ash, we mix fly ash with slags, and then we see that the reduction of the cost is quite remarkable. So our next achievement actually can only be realized if we find the best composition of raw materials, of as we call it, a blended raw materials. So for example, if we use, say, 30% of kaolin or metakaolin mixed with 70% of fly ash, or even we can use also slags inside. So three materials combined together, blended together to be a geopolymer. With that, the compensation of the cost will be much better and cheaper compare if we just use one particular raw materials, especially if we use metakaolin, because even though the metakaolin is a pure aluminosilicate compared to fly ash, but to convert kaolin into metakaolin in a large volume, it costs us a lot of money. That's make this materials is not feasible for large applications. So that's the answer, Professor.
Thank you, Doctor, for the questions. And we have one participant raising up hand. TS Wan Arif, silakan.
Assalamualaikum, Prof. Subaer, apa khabar? Sihat?
Alhamdulillah, terima kasih sehat.
Thank you for the presentation. It's quite nice, basically. I saw in your first pages on your presentation that you also explore on the incorporation of hydroxyapatite in geopolymer. So basically, how far it can go right now in terms of the performance? So is it basically you are looking in the hydroxyapatite dominance, or you are looking for the geopolymerization or geopolymer itself?
Sitting beside me, actually, my students who are dealing with the production of hydroxyapatite and incorporated with, at the moment, we incorporated with nano gold. But the main goal, actually, main goal of the incorporation of hydroxyapatite into a geopolymer network, we will use that materials as a filter for organic and inorganic species, especially in the production of membrane. So we will use as a membrane to separate the salt from the seawater. So the incorporation of hydroxyapatite in a right percentage should be able to reduce the salt up to 70%. And then combined with the graphene together, then we should be able to reach around 90% reduction of this salt from the seawater. So last time we produced the geopolymer hydroxyapatite composite, we use as an antibacterial surface. But now we will move further in order to use hydroxyapatite as an agent for filtering the salt from the seawater. So we already produced that kind of materials and in the membranes, so we are ready to apply once of our new perforation systems complete. Then we will try to use that material for separating salt or changing the seawater into fresh water.
Okay, Prof.
Okay.
Thank you. Now we have one last question to Dr. Subaer, our speaker. Now it's from the chat box from Dr. Pilomina. Good morning, Doctor. I have one question. What is your opinion on MK-based geopolymer? I believe this is metakaolin. MK-based geopolymer in the application of wastewater treatment. What is your opinion?
Okay. I won gold medals in Bangkok in 2020, in February in 2020, for using metakaolin-based geopolymer membranes. I still remember that, Prof. Mustafa. We got 2 medals presented by Professor Che. I don't remember his full name. In 2020. So a metakaolin-based geopolymer can be a apply as a very good filter or membranes for wastewater treatment. All right. So if we can produce the right composition, then you will have a very effective, very efficient membrane in order to separate between the organic materials from the body of the water into a fresh and drinkable water. I think one of these Professor Hamza's students as well now are dealing with the production of metakaolin-based geopolymer as a membrane for other purposes. So metakaolin-based membrane can be applied as a very high quality membrane for wastewater production. Wastewater treatment. So I recommend that please continue that study. Then you will eventually find the best way to produce. You can use actually hollow membranes or even just a flat membranes for that purpose. But I recommend that if you can produce hollow membranes, that will be much better. But the the techniques to produce a hollow membranes is much more difficult than use a flat membrane. But I can see that the students of Professor Hamza use a flat membrane and also produce a good result. So there's no problem actually in terms of the type of the membranes that you use. But the materials like metakaolin should be as pure as possible. So try to find a good metakaolin which less quartz, less anatase and other stuff in order to produce pure geopolymer. That's the answer.
All right. So thank you very much again to Dr. Subaer. I believe that we have plenty more questions coming up, but I know where you can find our speaker. You can email Dr. Subaer rightfully through his email address, as well as you can search for his research kit and so on. Yes, it is a promising material, this geopolymer. It can be applied anywhere, and even Dr. Subaer just mentioned it's even in wastewater application. It is unbelievably excellent. So I hope that Dr. Philomena also can try to explore more and try to collaborate with our speaker as well for future works, inshallah. Okay, now we have come to the end of our session. As a sign of our appreciation, we would like to hand you, Dr. Subaer, a certificate of appreciation. But because of we are doing it now online, so we appreciate if you can accept this digital certificate from our side. The president asked me to display to you this certificate, and inshallah will be handed over to you from him in a minute from now. So allow me to share my presentation slide just for a few seconds. So thank you very much, Dr. Subaer. This is the certificate that will be sent to you shortly as a sign of appreciation from our side here for your commitment as an invited speaker in this session 2, 20 and 22.
Thank you so much, Bapak.
Terima kasih Pak. Mohon doanya supaya perjalanan ke Makkah
InsyaAllah.
berjalan dengan baik, selamat pulang pergi.
Amin, insyaAllah. Barakah.
Nanti kita saling mendoakan gitu. Amin.
Mohon doanya. Siap, Pak.
Insyaallah, Prof.
So diharap semuanya isi ruang chat box telah disediakan link kehadiran. Till then, inshallah, see you again in the next session of my Geopolymer sharing series. So let's postpone our session, inshallah, to the next raya by reciting Tasbih Kafarah and Surah Al-As. Bismillahirrahmanirrahim. Illa ladina amanu wa amilus salihati. Okay. Semoga dimudahkan semuanya Dr. Subaer untuk menunaikan ibadah.
Amin. Amin.
Okey, assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Warahmatullahi
Terima kasih semua.
Terima kasih Pak.
Terima kasih.
Jumpa lagi insyaAllah lepas raya. Assalamualaikum.
InsyaAllah.
Waalaikumsalam warahmatullahi wabarakatuh.